Good evening, everyone. Welcome to the webinar. Today, we're going to talk about program-aided prompting and integrating the LLMs with code execution. So, LLMs, large language models, are great at language, but shaky when it comes to arithmetic, data wrangling, and exactness. So, the idea behind is let the model write small snippets of code and run them to check itself. What exactly is program aided prompting? So, program aided prompting, PAP, is a prompting pattern where the model proposes the code and then we execute it, and the results are given as the feedback. So, the model will finalize the answer. Think of it as a tiny single tool agent, one tool Python REPL. The benefits are plenty. So, to begin with, it's accuracy when it comes to math and data tasks, transparency, you can audit the code for yourself. Then you have reusability, same tool for many different questions. And how, what exactly is the design pattern, right? So, the prompt style is the first thing. You ask the model to produce a single Python block inside Python when it needs computation. Then the next one would be an executor where your script safely runs that block in a restricted namespace. For example, math, pandas, numpy, some scipy, and captures results or stands out. Then we have the loop, which is optional. Let the model revise once if the execution has failed. Ultimately, safety and guardrails. So, timeouts or any sort of restricted built-ins, small whitelist of libraries we need to keep with us. Strip file or network access, no import or no open, caption iterations and output length. When exactly do we use this PAP, right? So we use it when we're trying to do some sort of arithmetic tasks, stats, data cleanup, unit conversion, finance or operations back of the envelope. And what we need to avoid is tasks which need web access or untrusted OS calls unless you sandbox the further. And now we're going to talk about an example code that I have here, which demonstrates the PAP, right? Okay, so let's go on a section by section walkthrough of the script and what it does, why each part exists, and what all we need to be aware of. So the first one is setup and environment printouts, where we are going to, install the required libraries and import few required libraries. So you have Torch, which again we require for hardware and data types, transformers for Hugging Face models and pipelines. Warnings are muted out to keep the output quite tidy. And then the hardware information. So you print the PyTorch version, whether CUDA is available and GPU name if present. This helps you quickly see if you're on CPU or GPU and what precision you can safely use. Then we come to the model loading, which is from Hugging Face. And the model choice that we have taken is Microsoft Dialog GPT, which is a medium, so which is trained on around 345 million param dialog models. It's lightweight and will generate, but it is not pre-tamed to write the Python. So PAL performance will be hit or miss compared with the code and instruction models. Then we have the tokenizer. So loaded with auto tokenizer. If the tokenizer has no pad token, you can set it to EOS token to avoid padding errors. Then we're finally loading the model, auto model for casual LLM. And Torch D type float 16 on GPU and float 32 on CPU. Device map is given as auto. Only if CUDA is available, it will take. Otherwise, none. Then pipeline, obviously we need to do the text generation on pipeline. So we have taken this, and maximum length of the pipeline would be 400 tokens. It can generate, and temperature I've taken as 0.7 to allow for creativity. Then setting the sample as true. This will print a success message once it's loaded. Then comes the PAL core, which is your program aided prompting core. We create a small framework that basically prompts the model to write the code, then extracts the code from the model's text. It executes it safely and then attempts simple auto fixes if execution fails. We build a structured instruction over here, okay, where we give a sort of a problem and then we build the code. So we have something called as extracting the code from text, which splits the generated text into lines and tries to keep only code looking lines. Important caveat, basically once it thinks the code has started, it appends all subsequent lines. That means narrative text after code might be included. It also never explicitly looks for closing backticks. This can cause noisy extra lines in the code. And ultimately, to execute the code safely, yeah, to execute the code safely, we have constructs very restricted built-ins, only the basic functions and types, and it will execute the code with safe globals. So this is restricted, but not a true sandbox. And end to end, if I can see the flow, it will print the problem. It will build a code forward prompt. It calls the generator with slightly different decoding settings, where maximum length is around 350. And it prints the extracted code and executes it. On error, it will try to fix the common code issues. On success, it will return the captured output. Finally, we have initializing the examples. So here, if you see initializing and giving the examples, we're trying about basically 4 example problems: apples, temperatures, trying to get a compound interest, rectangle geometry, etc. For each example, it will generate the code, it will extract, execute, and print the output or the error. Because the dialog GPT isn't code tuned, you might get prose or incorrect code. Your fixed routine may help, but reliability varies. Then finally, we have step 5, which is enhanced PAL, where we solve with validation a particular problem. And we say get success rate. And we're also batch testing 4 problem types, which are arithmetic problem, and then a logical problem, and then followed by that a mathematics problem, right? And then followed by that statistics related problem, right? And we're doing a batch test of all of these. And ultimately, we're going to interact with the demo function. And then you have the implementation part. And here it's just a comparison with PAL versus the traditional COT chain of thought. It asks the same generator to produce text, reasoning, and returns the portion after the step-by-step maker. This simulates a free-form chain of thought style, not guaranteed to calculate correctly. So how do you compare these two? If you have a test problem saying speed is equal to 120 kilometers by 2 hours, you print both COT text and the PAL attempt, then summarize. So what COT will do, chain of thought, the text reasoning may make arithmetic mistakes, but the PAL, it will execute the code, usually numerically correct, when code compiles and runs. Okay. And we can make certain practical notes over here, where you load a small HF, right, text and model, wrap it in a pipeline, and then define your PAL helper that will prompt for Python, extract code from the model's text, executes it in a restricted environment. It tries small fixes when execution fails. And you have added an enhanced PAL with retries and success rate tracking. You can run a lot of examples and compare your PL output to the COT output style generation and integrate LLMs with the prompting aided action. So this is about the webinar today. Thank you so much for joining us. Next week, we'll bring in more exciting topics.